Hey everyone, in this video, we will solve a classic rotational motion question. A bullet hitting and sticking to the rim of rotating disc. Let's find out what is conserved and what the final angular velocity will be. First of all guys, I want you to read the question carefully and understand what the question wants us to do. Let's read the question carefully. A bullet of mass, we call it m, moving at horizontal velocity v strikes and sticks to the rim of a wheel, a solid disk of mass m, radius r, uncharted at its center, initially at rest, but free to rotate. This is important. Which of energy, momentum, and angular momentum is conserved for the bullet wheel system? Give a few words of explanation. Find omega and the final angular velocity of the wheel. Okay guys, first of all, we are going to understand the energy. There is a potential energy, but we are not going to discuss about this because potential energy is like not that important in this question, because we can say that this is a zero and there is a no potential energy, something like this. That's why potential energy is not that important at all. But kinetic energy is really important. Initially, we have kinetic energy, and we call it 1 divided by 2 mv square. There is a kinetic energy, but there is a collision, and we can say the delta kinetic energy is equal the final kinetic energy minus initial kinetic energy. We call it initial, okay? Initial. And we can write the initial kinetic energy 1 divided by 2 m v square minus 1 divided by 2 m from the wheel plus m from the bullet, and we have a velocity. But guys, as you can see, you can say that these quantities are bigger than these quantities, but this is not, because these two velocity is not equal. Let's call it this velocity v prime, or not call it v prime. We should call it v final, velocity final, and we call it velocity initially. And this velocity is too low. That's why the final kinetic energy is less than initial kinetic energy. This is this function, this equation shows us the algebraic quantities, and we can say that this is an inelastic collision because the bullet sticks to the wheel, kinetic energy is lost, converted into heat and sound during the impact. Okay, we call it, right? End of the day, we can say it, energy is not conserved. Okay, the other quantity, momentum. Okay, guys, we this is an linear momentum, and we write this like that, equal m times v. We have momentum. Why? We can see there's an m, there's an v. That's why we have momentum. But when the bullet hit the wheel won't go to the other side. That's why, let's write the final momentum. There is a m from bullet. There is a under m from wheel. And there is a final velocity. This is not moving to the other side. This is not moving to the right side. That's why final v equal 0. Then the final momentum is 0. Why it is not moving to the other side? Imagine that, guys. There is a stick in the center of the disc. And hold the wheel. Do not let move to the other side. Do not let move away. And there is a reaction force from there. When bullet hit there, and there is a reaction force. And we can see that there is a momentum, but for a while there is no momentum. Then the momentum is not conserved. Let's write there. Kinetic energy is not conserved. Momentum is not conserved. Let's look at the angular momentum. Guys, I want you to understand there is a two torque in this equation. In this question, sorry. One of them is when the bullet hits the wheel and the wheel starts to spin to the right side. There is a torque because there is a spin in the wheel. The another torque is external torque. The external torque need to be 0 because the wheel is not moving to the right side. That's why external torque is 0. Let's call it external torque equal when the bullet hit there will a reaction force, but the bullet hit there was a force in there. There was a force and minus reaction force, reaction, and we call it, R. If there is 0, the external torque is 0. Guys, you should know this. If net external torque is 0, the angular momentum is conserved. I'm saying that again. If there is no external torque acting a body, acting on system, the angular momentum is conserved. Okay, we said that the angular momentum is conserved. But this is asking us to find out what is omega and final angular velocity. Okay, if the angular momentum is conserved, we can say that mv r angular momentum initial angular momentum have to be equal final angular momentum. Inertia total and omega. Okay, guys. Now we write down this. MVR equal momentum of inertia omega. What is momentum of inertia? In this question needs to give us, but this is not give us. But I will write this. What is the inertia of momentum of inertia of a wheel and bullet? We cannot find out the momentum of inertia of a bullet, but we assume that this is not a bullet. This is a mathematical point and have a mass and moving to the right side. We assume that, guys, okay? And we can write down like this: m r square plus, this is momentum of inertia of bullet, and 1 divided by 2 m, sorry, this is not like this, m r square omega equal m v r. Okay, guys, let's write down this as simple as we can. V omega mvr mv equal omega. We don't need them in it. Let's kick them to the right side, left side, and write down m plus 1 2 omega. Okay, we find out what the omega is, and we need to find out angular velocity. Angular velocity equal omega times r. We know omega, we know r. Let's write down this. Angular velocity equal m v r m plus 1 divided by 2 m r, and these r's are gone. The last equation of velocity of angular velocity m times v divided by m plus m. Guys, as you can see that this angular velocity is smaller than initial velocity. That's why we said the kinetic energy is decreased. Okay? And we write this like that. Okay, guys, we finished the question. And if you like the question, and if you understand or didn't understand any part of this question, you can ask me on the comment in the comments, and please subscribe and like the video.